twist on the Lagrangian sphere. I know last week Brian talked a bit after the talk, so we will revise again. We will go through the setup again today. So let us consider the cotangent bundle, which is an famous example in symplectic geometry. Cotangent bundle of Sn, and then let L be the canonical Liouville form. Okay, let me say few words about the reference today. So today reference would be a paper by Oba. So I'm following his setup. This paper is called a higher dimensional contact manifold.
Could you just bring the page down a little bit?
Sorry?
Could you just bring the, I can't see the, I can see contact manifolds, but not anything above it.
Oh, eh? And any other see?
We are fine.
Other see?
I think I can see that. Maybe
Okay.
it's to Peter. Maybe your
Okay.
It should be the same.
Yeah, it's my iPad.
Oh, iPad. Okay, let me write lower.
Sorry.
Okay. How about now?
Yeah, I can just see that. Yeah.
Just see that?
Yeah.
Right lower. Then can you see the title just now? Then twist.
No, but
No?
I can see the line underneath it, but I wrote it down before anyway. Okay,
Oh,
yeah,
okay, sure.
I can see that easily. Thank you.
Okay, sure. So it's higher dimensional contact manifold with infinite many Stein filling. So I'm following the setup here, and I will cite along the top. I will cite a lot of Seidel's paper, various paper. Okay. So let's go back to the setup again. So does everyone know about Liouville form? Should I remind everyone? Okay. So just briefly remind everyone what's a Liouville form. So let's say you got a cotangent bundle M, and S1 to Sn plus 1, let's say, is the coordinate function on M, and dx1 up to dxn plus 1 is the coordinate on the cotangent space. So let's say we relabel them because we want to talk about one form, right? So we relabel them first. So a general one form on this cotangent bundle would looks like something like this. Okay, where beta I and beta I tilde would be smooth function. And Liouville one form is something like you take your beta I to be psi I, and then let beta I tilde to be 0. And wait. Then you can write your Liouville one form as this. Okay, and in this case, we can see that in our case, if we write our cotangent bundle with the following coordinate. We can see that we can write lambda to be P dq. Okay. And then also from last time, we also look at the zero section. Maybe write down zero section. Okay, say psi is the section map, global section. And this then is Lagrangian in our cotangent bundle. Okay, so Lagrangian's meaning half dimension of having half dimension of your original space, and if you consider the area form, so this area form is getting obtained from the one form. So let's say, so these are the subset of your manifold such that when you compute the area form, it's 0. Okay, so just a reminder of Lagrangian. Okay, so you might wonder, last time I talked about the so let's go back. So last time I talked about the fiber from the Muno fiber, If you look at the fiber, say this square plus dot 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 plus Sn minus 1 square equal to HW. If you remember from last time, we said that this is symplectically isomorphic to a cotangent bundle, right? Today I can show you, for example, how the isomorphism work. So let's say we look at when minus HWZ equal to 1. Okay, so we look at this particular fiber here. So this particular fiber, you can write as this. Okay, and if you do some coordinate change, let's say xi, let's let xi to be equal to pi plus, I don't put I because later you confuse with the complex imaginary number. So I put let's say put a I q a. Okay. So if you do this kind of a change of coordinate, you can write your set as this. So p plus I q p q. Okay, so you are just turning the equation here into the equation here. Okay, and then from here, maybe it's easier to build the isomorphism. So the isomorphism is, if it is not wrong, it is like this. So it's p q p. Okay, of course you need to check whether it's satisfied, like if this thing is equivalent to the top. Okay, I think I don't have laser. Never mind. Okay. Any question? If not, then we go to the next one. Okay, so Peter can only see here, right? Starting from here. Peter?
Yeah, I can see that and a little bit above that.
Okay, a little bit of, okay, sure.
So,
Okay. Now we look at a Hamiltonian function which Brian talked a bit about last time. Okay, sure. Okay, thank you.
I can see that.
Yeah, sure. I saw you. Okay. Consider a Hamiltonian function. So Hamiltonian function is like a smooth function. Okay. Why we call it a Hamiltonian? Because we can build a Hamiltonian vector field from it. So how to get this vector field associated to this Hamiltonian function is okay, recall. So Hamiltonian vector field is going from the tangent cotangent bundle, the manifold to its tangent space. And then how do you find it? You go and take your area form and then contract with your vector field. And then this should be the same as your apply D on your mu. And then these two functions should agree. And then you will get from this, you should calculate this to be this thing here. So this is the vector field associated to the Hamiltonian flow. Okay, and since we got this vector field, we can integrate this vector field. So integrating this vector field will get a flow.
So where is the second term from?
Yep.
Where is the second term?
This one? You mean
second
this,
term in the
this term?
yeah.
This term? I actually didn't do the computation, but they write it down.
We can do just in one dimension. N is one. So PQ, because if you take a function, just take any function.
N is 1, so you get this.
N is 1. Okay.
N is 1, yep.
Is that true? I mean, if you look at the function, okay, so maybe the Q, because the function doesn't depend on Q.
You mean this
if
one?
you look at the omega, maybe this is dp. What is omega?
Omega is the d of lambda. So lambda is the
okay, so maybe
view one form.
Let me go back. What is lambda in this case? Okay, maybe lambda.
Let me go back. So the lambda is p dq.
Okay. So you have this Q. This map. Okay, so this map is x is p plus iq. And the function is p. Okay, so it's function in p and q. If we change. Okay, maybe this change.
Change the.
Okay. That's term. Yeah, I think maybe just there's the coordinate change.
Oh, okay.
Yeah.
Okay. So integrate this flow, you get integrate this vector field, you will get a flow. And then if you look at this flow on your base space, so start with point, and then you project to Sn. Is that, I think is correct. Project to Sn, then you will see that you are starting on a point Q, and then move with P. Move with the velocity vector P over the norm P. Okay, and you can see that the orbit of this floor is a 2 pi periodic closed circle. And so this is a periodic closed circle, and we will get, from here, we get a Hamiltonian x1 action on T x. Okay, and then this formula is, I think it's quite familiar from last week. So this formula is PQ cos TQ plus sine TP over P equals, and then comma minus P sine Q plus cos TP. Okay. Okay, so yeah. So by Hamiltonian, x1 action is just mean one parameter subgroup, and also the integral of Hamiltonian vector field. Okay, so this is what x1 action means. And in this case, Hamiltonian. And in this case, this function will also call it a moment map. Okay. And then, okay, so the reference for this formula, I think the first time coming out is from Seidel PhD thesis. So Seidel flow homology.
I can't see that either.
Can't see that. Okay. I move it. Maybe move it here.
Yeah. Why does everyone else be able to see this? This is
maybe I move it here. So here. Okay, Seidel.
This is the bottom of what I can see.
Oh, okay, sure. Okay, sure. Seidel PhD thesis flow homology and symplectic isotropy problem. Okay. So notice that this formula is only defined away from zero section. It's like what Brandon said last time. You can extend this map. So if you compute at time t equal to pi, it's actually an antipolar map on Sn. Okay, so if you plug pi in, then what you get is pi pq is minus p minus q. Okay, so yeah. So yeah, on the zero section, you define as the antipolar map, and then the other section you apply this kind of Hamiltonian S1 action. Yep. Okay. So finally, okay, before, okay, so I think the diagram should be something like this. So and then you extend to an antipode limit. Okay. What else? Okay. So now we're going to define what's called a modal Dehn twist. So we need a cutoff function first. So I think this is a bit too high. It's down.
Thanks.
Maybe go back to the first, the previous page. There's something wrong with if you evaluate the pi.
Evaluate the pi.
If you evaluate pi, cosine pi is minus.
Oh, minus q, is it?
Minus q. Something minus q and.
Minus q, and then.
And then this is minus p, right? Is that and put them up? Is that?
Did I write something wrong? No.
Is that restrict to the involution? There's something wrong in that.
Something wrong because this guy is a bit weird. Okay. Because
if you set t is pi, if you t is pi, right? So then you send the pq to minus q minus p.
Yeah, right.
And
I think maybe this q and p have to swap.
It's very windy outside. I'll move inside. Okay, you can continue. I just think that if we t is pi, certainly is not.
It's not.
It's in the PQ.
Yeah. Yeah.
Okay.
I think I get what you mean. Maybe need to do some modification to this formula, because I think when he defined this P and Q, he's kind of like swap the normal P and Q.
Okay.
So I think I think there's some confusion here. I think maybe in the formula P and Q have to swap to get minus P and minus Q. Is it? You agree?
Yeah, okay. I think let's just do the example. I say that is just Dehn twist. It's but kind of with very strange looking.
Let me see.
Alright, maybe the PQ Q is the coordinates.
Yeah, sorry. P and Q should swap. P and Q should swap. If I look at the Seidel paper.
Oh really?
Yeah. Okay. P and Q should swap.
Seidel thesis?
Seidel thesis. Yeah. Yeah, P and Q should swap. So this is a U is a P is a Q. And then cos V is a Q. Yeah, this one, okay. Minus P minus Q. Correct or not? This one is a V Q. So this one wrong again. This is P. This is Q. This is Q. Yeah, so cos pi minus P, and then cos pi minus Q. Okay. Yep. Okay, so let's take a cutoff function. So cutoff function is smooth. Such that for t, and then 5t for large is 0 for large t. Okay, then model, then twist. Tau is defined to be tau x. So you should apply the cow function inside your x1 action, and then antipode the map on the. Okay, I haven't tell you what's A, right? So where A is the anti. Okay, so the theorem is this is the simplex automorphism of. So that means it preserves the is a diffeomorphism, and it preserves the area form. Okay. Any question?
Function. The function,
Mm-hmm.
you only need the function defined on the positive t.
Positive t.
I mean, because you only apply cosine to the norm. So why you need cosine t plus cosine minus t is 2 pi. So that means because if t is 0, we essentially say that, so I can choose any function which is smooth, which is t0 is pi, and t beyond beyond half or 1 will be 0, and that will be fine. And that's, I don't see any kind of symmetry. If you look at symmetry, cosine t plus cosine minus t is 2 pi. So kind of to be tried to, you only, if you look at the domain of actual definition, you only apply this psi to the norm
positive
x, norm of x. What do you mean by norm of x?
Norm of x.
I think there's some. X should be, there should be 2 coordinates, right? Some like p and q before. Now it's just changed to x.
Because
but is when this some kind of very strange looking. I mean, tau is defined cotangent bundle, and then just take tau is x.
I think I get what you mean.
X is, so essentially a norm in the p in the cotangent direction. So if x is not equal to, maybe he's doing something strange.
But the norm of p is always 1, right? So you just look at the Sn part.
What do you mean p? P is cotangent direction. P. That p is okay. Your p here. Q. Something is 1. So p. Which coordinates is the base? Okay, you think p. What's that?
P is the base. P is the
it's
base.
very strange. P square norm, which norm is 1?
I think P is the base.
P is the base? Okay, if P
so.
is the base,
I think P
but
is the
Q
base.
has norm 1.
Q has norm 1. Q has norm 1.
Okay, when I say P with the first coordinate or second coordinate, second coordinate is.
I think this one is base.
Does that mean you
Is it right?
change the last little bit from norm Q equals to 1 to norm P equals to 1 then?
So base.
If you want P.
Okay. So okay. Okay. In that case, then Q is the base. Q is the base. Q is the base.
Q is the base. Okay.
Yeah, that's why I think this guy swapped the.
I also mean, if you look at the X, look at the tau, but essentially, as I say, that you can just look at the function which is a norm of the cotangent vector. I mean, you can't say if X not belong to, what do you mean by X not belong to Sn? I mean, Xn is a zero section. If not zero section, then what is all going to look at the norm? You have two components. One is Sn, the other is. But essentially, you can see that if you close to the Sn, I mean, if it's zero section, it is antipomorph. And then away from zero section, getting bigger and bigger, there will be the identity. So it's like compact supported. Away from zero section, far away from zero section, it is identity. So if you look at the Dehn twist, the blue line you are drawing, the top bit and the bottom bit doesn't change. It's a straight line. So that is identity.
Okay, yeah.
So that means it's only in the cotangent direction. So the maybe it's X is Sn, and then you have P, so XP. So P is 0 is AX. Then P is not 0, and then you should be psi norm of P. Right? Because away from 0 section, that's cotangent vector. So cotangent vector, so maybe I'll just
you can draw.
You can draw.
You can draw. You can go view option and then
view.
Yeah.
Maybe.
You using laptop?
I use the laptop or view option. Okay.
Yeah.
So top.
View option. Yeah. Now and then you can annotate.
Oh, I see.
Yeah.
So I mean that if we just like a function which is doesn't matter because I can take this is pi, and then whatever the function which is like make it constant here, and then go smoothly, and say so this is say 1, and then here then I just apply E and then I and psi. And then norm of the P. P is the cotangent vector. Is that true? Maybe other pi. Okay, so maybe. Oh, it's other way around. Maybe P. I want a P0. P0. P0 is identity. Yeah, P is 1. I need P1 is. Oh, that maybe the. Oh, that's very strange. What's this? So this is
Why?
T. Okay, T when T0 is pi, and then okay, so I think this is correct. Okay, so this is when P is greater than 1, it is 0. Right? So then I apply this. Right? So I can just So this is what, so here x, when you say, I mean, here it should be, there's two components. So maybe like x and then p. And then here I say the p, if p is not 0, and then here p is 0.
P0, P0.
Yeah, p is 0, and then psi 0 is pi, and then is antipymap. So this this is when this actually it continues when p towards 0, and this thing is this is towards a antipymap. So maybe
so the cotangent vector at the 0 section is 0. The length of the cotangent vector.
Yeah, a p is cotangent in normal direction.
Yeah, I think that the norm of x in this formula means the norm on the cotangent bundle. So the points on the 0 section have norm 0.
Oh, okay.
Right.
So it grows when it go up. Oh, okay.
Yeah.
And then, okay, so if you think a lot, if we did that way, okay, so then I won't say that you just take any function like this. I mean, there's no need to this kind of redundant because we don't really need a symmetry at a negative t because that's not appearing. I mean, in terms of mathematics, that condition is redundant. I mean, you don't really need this condition. We only need because we only the domain. You can see the domain is the norm of x. Actually, we only look at the domain is positive part. So there's no need to look at I mean, what gain. I mean, there's nothing to do with psi is minus t, right? So I mean, it looks like a very strange looking. You choose psi t and plus psi minus t is 2 pi, kind of symmetry. If you do that, and then what is the function will be adding is 2 pi, then because then so here is pi, and then use the symmetry. Essentially, it will be pi, and then going up, and then this will be 2 pi. So this will be 2 pi here. Right, so it's function like this. But I mean, here is less. We don't need the lective part. I mean, there's nothing to do with. So I think this is like a. I mean, of course, you can do this, but to be, I mean, it's unnecessary. I mean, you maybe try to show off. You can construct a function globally on R and the symmetry. There's nothing about 2 pi. I mean, nothing about the symmetry. I'm saying that if using this condition, it just say that if we know the function on the positive part, the negative part is given by the identity. But on the other hand, there's no need to have function domain with selective t. So we never use selective t. So the whole thing is like I mean, we may just take as I draw here. So so this function will be enough. Anyway, maybe
but your function need to extend or not? Right.
No, it doesn't matter because phi we don't need the psi to define on the lective.
You mean reduce the domain?
No, this psi you already applied to the positive part, right? Here you already positive part, so nothing about.
So you're saying you just define function from the positive?
Yeah, just define function positive.
Oh.
Is that condition in the literature?
Yeah, but I mean that sometimes this is redundant, right? So if you want to be, if you can say that, I mean, I mean, just a similar story. Some people want to be impressed, and okay, that's just a story. Sometimes in the people say, suppose this T, for example, this T is big, and they will say, okay, this T. What I'm going to write maybe. So maybe say, so they say the T is greater than 10. And you may ask, why 10? Well, let's change it to 9. Right? So, so it's just like a play game, and that just make fun. That doesn't really matter, because this, I mean, sometimes there is estimate. I mean, if there sometimes just make fun. So let's choose T greater than 100. If you ask why 100, then do what about 200? It doesn't really matter. So here I can just take a very small, I mean, any function, and this actually some LSem is fine, because, and then this was supported away from radius. So that means if I define this, so maybe call this data. If I define this way, and then this tau, the restrict to the complement of the ball, the disk bundle of data of this cotangent bundle. And then you look at the complement of this, and this will be identity. Whatever the data doesn't really matter, because away if the radius, so this is a ball data ball in the normal Fabry direction. Away from this radius direction data, this will be time. So this is like time, the time per side. So this time will be 0, so it doesn't flow. So then it doesn't really matter where you choose. You can getting smaller and smaller. So make arbitrary close to 0 section. Anyway, so I will just say. Oh, sorry. Did I clean yours?
Don't. I think.
Okay.
No.
Okay. I can't clear. Actually,
you want to start a new one? I start a new one. I start a new one.
I think I should maybe undo.
I start a new one.
Okay. Sorry. I thought that if I clear mine, just not yours writing.
Oh, I'm not sure.
Okay, maybe I just
never mind. It's okay.
Erase.
It's okay. It's okay. Never mind. Should be fine.
Okay.
Okay. So we only define on the cotangent bundle on a local model. Next, we need to define on arbitrary Lagrangian n-sphere. So to do that, we just need to apply some trick. So it's like manifold theory. You need to put a chart on it. So in this case, they call it a framing. And then I think the n-sphere here really mean n-sphere, because you are in the 2n manifold. So we take a framing. If you want. Okay. And what else? So we say L1 is isotopic to L0 if there's this frame. So this is crucial to talk about when you want to consider isotopy between Lagrangian sphere. So you have a family of Lagrangian embedding. and isometry. Such that this family of embedding agree on the endpoint, agree with the framing, okay? And then suppose L is frame. So you have a Lagrangian sphere and then you got it frames. Then you can look at the Weinstein tubular neighborhood. You can go and find the Sn inside your Lagrangian sphere. So there's this an epsilon and symplectic embedding I from a disk of cotangent bundle into your W such that your I of Sn is equal to L, which is to look at the framing of your L. No, not framing of your framing of Sn. Okay, and then similarly, you also take the count function, and then because we already push it back to Tsn, so we can just define it as using the embedding. We can define a general Dehn twist on here. So we start with an arbitrary Lagrangian sphere, and then we push it back to Tsn, and then we do Dehn twist, and then we put it back again using the embedding. Put it back to the symplectic manifold. So when we say Dehn twist, so this is the general Dehn twist, generalized Dehn twist. So Dehn twist is TL from W. So in our case, this W you can thought of as the Mueller fiber defined by TLX.
Seng, what's that symbol you said? Dehn twist along L is what? What's that
Dehn
symbol?
twist along L is tau L.
Tau L. Oh, okay.
Tau L. Okay.
Thanks.
So you use your embedding, embed, go back to Tsn, do the model, then twist, and then push it back. Okay. So of course, this is an element in This is an element in sim of your symplectic manifold. And then of course, if you want to look at the mapping class group of this symplectomorphism, you need to show that this is independent on your embedding iota and also the cutoff function we picked just now. Okay. So do you want to still talk a little bit more about the monodromy on the
maybe just cover a little bit more.
A little bit, okay. I won't provide proof, but I will cover a bit.
We can always continue next time, but at least we want to make a bit of progress.
Yeah. So okay. So I talked about a bit how this Dehn twist will generate, or how you see it, how you view it from the viewpoint of the disk. So okay. So okay. I won't provide proof here because some of the proof is quite long. So this reference is this paper here. So a long exact sequence for symplectic for cohomology by side there as well. Okay, so inside there's a proposition 1.1.5. So consider so let's say CB is our critical point. So critical. Let's say we start from a point in the disk. Then we start from CA, and then we use C to reach CB. So that's why I call it a CB. So, and then you can also look at a loop around here. So they call it a doubling C. Sometimes you will see doubling C. Okay. So the proposition is like this. The monodromy around the loop is isotopic to the then twist, but along where? Along the vanishing cycle. But I haven't tell you what's the vanishing cycle here yet. I'll tell you in a moment. So put into symbol is the monodromy is equal to the tau along VC inside. So you should think of this vanishing cycle is some Lagrangian sphere, but I haven't tell you what is it. I will tell you in a moment. So let's say this is a symplectic, the Miller fiber along CA, because you go out from CA and then come back from CA. Okay. So actually from the Picard-List sheet theory, you will see that this kind of monodromy, if you leave it up to the fiber, it will give you a symplectomorphism from the starting fiber back to starting fiber again, because this is monodromy. Okay. So last time we talked about why you can do this is using the connection. So where do you get the connection? The connection you get is from the tangent space of your Mueller fibration. So remind again, Mueller fibration is your E, your big E, a collection of Mueller fiber. And then you can decompose into vertical and horizontal. Because this vertical is the kernel of your D pi. So pi is going from pi is coming from E to this. And then since this is the kernel, so this is the image. So this image will mesh up with the tangent space of D. So that's why you can take your tangent vector from your D and then move it out to E. Okay, so this is conceptually why you use the horizontal space here. Okay, and then so this is how you lift the monodromy up to Mueller fiber. How about this symplectic side? So this symplectic side, so this VC, okay. So this VC, this vanishing cycle should be a boundary of some ball. Okay, this is they prove it in this paper. So this is an exact Lagrangian, but I still haven't tell you what ball is it. So okay, so to talk about this ball, actually the thing you need to see is the path C, which we always see in the Picard-Lift shift theory, vanishing path. Okay, so how to form this ball? So so how to form this ball? So this ball is actually the set here. So maybe I can't quite picture this ball. Maybe Brian can see. So so actually we start from what? Start from a path C, from A to B, and then to D in this D in this case, and then C inverse of my critical point is just B. Okay, and then we just now also discuss about this. Let me write this first. So we also discuss about the parallel transport thing. So we have the parallel transport moving across along the fiber. Okay. Write down parallel transport. Okay. So how to take this ball? So the ball is taken to be the set of point in the middle fiber. Okay. And then this S should be coming from B to C, such that if you take limit of x prime going to B, every part of the path that converge to x. Does this set make sense or not? Actually, you have to union with your limit point. Brian, you see this set before?
No, maybe I'll just think about this. S is this power? Is that power transport? What?
Power transport.
Power transport. Well, that
Rho
is.
Is the point in the.
This is what we call the Lipschitz symbol, right?
Lipschitz symbol. I think so.
Yeah. So A, B, X to a B. So that is, so if if we fix S.
You fix X. Yep.
So that is a sphere, like is the Valensian cycles. All the Valensian cycles will limitate that term.
Okay.
So then this essentially it is again just a ball, like a cone, over the Valensian cycles, right?
M+1 ball.
Yeah. So center is x0, and the boundary is Valensian cycles for VC. But then twist.
What's x0? Sorry, quickly.
Sorry. I didn't tell you what S0 is. So S0 is should be
points.
The critical point. When you look at the critical point at the bottom,
moving side.
you have a critical point. You have the critical point